Hey y'all, Dr. G here. This video is a follow-up to the first video where we explored the general structure of nucleic acids. We talked about how there are three primary regions. The central sugar, which is characterized by the 2' position that can have a hydrogen or a hydroxyl. If it's a hydroxyl, it's ribose, and this is the form of the sugar for RNA or other cofactors that we'll talk about later in the semester. If it's a hydrogen, the reduced form, this is the form exclusively found in DNA. It's deoxyribose. Attached to the 1' carbon, right here, is our nitrogenous base. And attached to the 5' carbon is one or more phosphates. We label them the alpha, beta, or gamma phosphate depending upon how far away they are. Things to recognize here is that all of these are characterized by at least one negatively charged oxygen, and for the terminal one it's always 2. So this phosphate region brings functionality, it brings negative charge to it. In the video here we're going to explore the base structure a little bit more. Okay? And in the last video, we mentioned the idea that there are two classes of bases. There are purines and pyrimidines. The purines have a core 2-ring structure, while the pyrimidines have a core 1-ring structure. In this video, we're going to focus a little bit more about how to draw these things and how to recognize them. Okay? The purines we'll start with. These are the 2-ring systems. And all of them have a core structure of nitrogen, carbon, nitrogen for the first ring. Okay? So nitrogen, carbon, nitrogen. This is where ribose attaches to. There's always double bond here and here. All of the purines have this core structure for the 5-membered ring, and then it extends to the 6-membered ring. Nitrogen, carbon, nitrogen, and then close it up with carbons. Okay? Every single purine has this core structure. Okay? In addition, there's also a lone pair hanging out here. All right, so now what we need to think about is what gets attached to it. And for me, the way that really makes sense to me is to remember that adenosine A has an amine up. So pointing up off of this second ring is an amine, NH2. Okay? That's really helpful because at this point we have everything decorating the ring system that we need. Now what we need to do is to fill in double bonds to make sure that everything has a complete octet. So this nitrogen has a lone pair here, so we need a double bond. This nitrogen has a lone pair, so we need a double bond. Once we've done that, everything has a complete octet, and this is the structure of adenosine. Okay? We can do a really similar thing for guanine. Nitrogen, carbon, nitrogen, close it up. Double bond, double bond. Nitrogen, carbon, nitrogen, close it up. Okay? Ribose attaches here. Now, with guanine, instead of having an amine pointing up, the other option is a carbonyl. So we have a carbonyl pointing up in this position, and at this position, we have an NH2. Okay? Now we need to think about what's going on to complete octets. So we need a double bond here to complete the octet. This nitrogen has a lone pair here, and it has an NH. Okay, this is the only way to get an octet for this nitrogen. This is guanine, so here we have G. Okay? Being able to draw these is really helpful. The other thing that I think is very, very helpful is being able to recognize and remember the hydrogen bonding pattern. Okay, because that, at least for me, is really helpful when trying to draw the pyrimidines. Okay? So it's this side of the molecule. This is the face that makes hydrogen bonds in Watson and Crick base pairing. So what I want you to recognize is that with adenosine, we have a hydrogen bond donor at this position, an acceptor at this position. right? This nitrogen can accept a lone pair. This nitrogen can donate a lone pair. And there's nothing present here, so there's nothing that we care about. The two hydrogen bonds that AT make are at this position, NH2 here and the nitrogen here. So it's a DA pattern for adenosine. For guanine, acceptor, donor, donor. This carbonyl is a hydrogen bond acceptor. This nitrogen is a hydrogen bond donor, and this hydrogen is a hydrogen bond donor. Okay, so being able to recognize those patterns is going to make drawing the pyrimidines a lot easier. Let's see why. Okay, so the pyrimidines are a single ring structure. Still the same kind of pattern. Nitrogen, carbon, nitrogen, and now close them up. Notice this six-membered ring looks the same as this six-membered ring on our purines. Ribose is attached here. Two other things you can immediately add to every single pyrimidine. A double bond here and a carbonyl here. All of them have that. Okay? Now what we need to think about is the hydrogen bonding pattern. Okay? So adenosine has a hydrogen bond donor here, a hydrogen bond acceptor here. So the complement would be an acceptor right here and a donor right here. That's what we need thymine to have, an acceptor at that position and a donor at that middle position. Okay? So a hydrogen bond acceptor is a carbonyl. A hydrogen bond donor in this hydrogen must be an NH. So this makes this oxygen a hydrogen bond donor. It makes this hydrogen a hydrogen bond, acceptor and donor. That pattern matches what's needed to make a Watson and Crick base pair with adenosine. This would be thymine if we have a methyl group here. If we don't have that methyl group and that's just a hydrogen, then that's uracil. But for DNA, we always have this methyl group here, making it thymine. Okay, let's draw cytosine. It's the same core structure. Nitrogen, carbon, nitrogen. Close up the six-membered ring exactly as we see in thymine or the six-membered ring in our purines. Ribose attaches here. Double bond, carbonyl. Now let's think about the base pairing pattern. For guanine, we have acceptor, donor, donor. So for cytosine, we need donor, acceptor, acceptor. So if we think about a donor, this must be NH2 at this position. That will hydrogen bond with the acceptor, carbonyl on guanine. We need an acceptor at the middle position, so this must be a lone pair. And we need an acceptor at this bottom position, which we already have in our oxygen. The last thing we need to do is to complete the octet, because this carbon right now doesn't have an octet. Make a double bond, and now we have an octet. I have a hydrogen bond donor, acceptor, acceptor, and that's the pattern that we need to complement guanine. Okay, so if you focus in on those themes, right? The nitrogen, carbon, nitrogen theme, the base pairing pattern theme, then it makes drawing these and recognizing these a lot easier. All right, the last thing that I want to point out is the idea of base planarity. Okay, so these nitrogenous bases are all planar, and that's because the atoms are all sp2 hybridized. And for most of them, it's really easy to see that, right? This carbon is sp2 hybridized. This carbon is sp2 hybridized. It's really easy to see how most of them are sp2 hybridized. However, a couple of these, it's a little bit, it's hard to see that, right? Because we think this nitrogen, for example, it sure looks sp3. But in reality, because this lone pair is part of the resonance form of this ring system, they're built into the pi system. So Despite the fact that this looks sp3, it is planar because of resonance, okay, making all of these bases planar, and that's really important in the structure of DNA helices. In the next video, we'll explore how nucleic acids condense to form polynucleic acids, DNA and RNA.